record here. Welcome everybody. I hope everyone is doing well. Today's going to be a little bit more lecture style than the Q&As have been in the past. Maybe if we have a little bit of time toward the end, I'll have a couple of questions for you, but I want to make sure that we can finish up our third of the three big linear models here, and that's electrical circuits. So we're going to spend the first part of class talking about electrical circuits, and then I'm hoping I can spend the last 10 or 15 minutes or so talking about how we come up with the thing called an integrating factor, the thing I used to solve Newton's model in class on Wednesday, Newton's law of cooling model. And then that'll give us all of Monday's class to just practice that integrating factor method, which one of the main methods for the course. That'll give us Monday's class to practice that a bunch in preparation for your skills quiz, which is due next Wednesday. So I did want to start, however, today by talking about your upcoming exam and the assignments you have due. Normally, over the weekend, you would have a Maple Lab due, but because this is a 2-week module, that Maple Lab's not due till next Wednesday night. We do have an exam a week from today, so rather than meeting online for a Q&A next Friday, we'll meet in class at the normal time to have the exam. So the exam will be covering all of chapter 1 except for section 1.4. The reason that I don't cover section 1.4, that's a numerical method known as Euler's method, is because we have a class called numerical analysis, or numerical methods, excuse me, and they talk about Euler's method in that class. So if you are interested in the material in there and you're interested in how to solve differential equations numerically the way the computer would, then numerical methods might be an interesting course for you to take. Since that is one of the topics in that course. But in talking about the material for this course, thinking about all the things we've gone through so far, it'll be pretty evenly weighted among the sections. There's not one section to me that really sticks out as having more material on the test than any other. So it is pretty evenly weighted. I do want to let you know that there is a take-home exam part of this. There are 2 Maple questions that you'll be given as part of your exam next Friday. So the way that'll work is you'll have the in-class exam on Friday. You'll take home the Maple stuff over that weekend. You won't have anything else due that weekend from this class. So your weekend will be free to be able to work on those 2 problems. So you'll work on those 2 Maple problems. They're similar to what we've had for the Maple labs. They're probably a little bit shorter actually than some of the Maple lab questions. But you'll work those 2 questions. They'll be modeling questions of some type that require you to use Maple. But you'll have a take-home exam, and that'll be due back in class. Well, that'll be due before class begins on Monday. You'll still upload it to the exam 1 assignment, just like you've uploaded all the other Maple labs. But that'll be part of the take-home. So I won't be able to finish grading your exams till the Wednesday after, because I'll have to wait for those take-home exams to come in. But the exam will have basically 2 different parts to it. You have what are called qualitative techniques, which is tell me something about the differential equation and or its solutions without actually solving it. So these are all techniques that we've talked about that relate to naming and basically what we call qualitative techniques. And I have sections listed for each of them with some numbers of problems out of the textbook for you to look at that are kind of similar. And then we also have analytic calculations for the in-class test, which is actually solving the differential equation or actually doing a solution of something. These are probably where most of your time will be spent studying. And I just have a couple of things here that fit into that category. The 2 major techniques from this first part of the course is separation of variables and integrating factors, which we'll talk about on Monday. So solving separable differential equations and solving differential equations. Someone have a question? And then these are the things you're expected to know for the Maple lab. On the Maple lab or on the Maple take-home part, the only restriction is you can't use people. So you can't talk to one another about the Maple take-home, but you can use your notes. You can use all the Maple files I have online. You just can't work with one another on that take-home portion of the exam. Do you have any questions about the layout for the exam or anything like that? All right, if y'all run into any questions as you're looking over material this weekend, feel free to bring that up on Monday in class. I'd be happy to address them. But let's talk about circuits today. So like I said, there's not going to be much Q&A to this today. It's going to feel more like a lecture, but I did want you to still have Learning Catalytics up so you can see some of this stuff as we go along. But I'm going to kind of talk through some of this stuff as well. So I'm curious, so if you'll put in chat so that I can see, how many of y'all have taken a circuits course or are currently enrolled in a circuits course? Okay, so roughly half the class. That's about what I've expected. So this is one of those topics that students that have some experience with electrical circuits previously just love this material because it's reinforcing something they're learning in another class. And for students that haven't taken a circuits course previously, this is one of those topics that's they don't struggle with, but they don't have the same foundation that other students do. So my goal today is to get everyone in the course comfortable with the terminologies here, because this is not the last time in this course that we'll see circuits. A big part of the course is understanding that there's no difference between a circuit problem and a mechanical problem, that mathematically those two things are the same. And over the course of the semester, I'll try to make that apparent to you. So today is about terminology, notation, and getting comfortable with the circuit. So I want to start by, we talked about Newton's law of cooling and how the physical law there manifested a differential equation. That's the one we looked at in Wednesday's class. Well, there's another physical law here for circuits that's going to create a differential equation. And it's something called Kirchhoff's law. And forgive me if I'm mispronouncing that. I've heard it pronounced at least 4 different ways. So Kirchhoff or Kirchhoff or Kirchhoff, I've heard it pronounced all those different ways. But Kirchhoff's law. And Kirchhoff's law states that if you apply a voltage source to a circuit, so this is your voltage source, or we sometimes call it an EMF, electromotive force. Basically, it's the thing that's going to push electrons through your circuit, okay? So whatever the voltage source is, it has to be equal to the voltage drops across each of the components of your circuit. So the kinds of circuits that we're going to be dealing with today are what are known as LRC circuits. So the picture that goes along with this is you've got some sort of resistor, you've got your battery, which is the electromotive force, you've got a coil, which is called the inductor, and you've got a capacitor. So let me label each of these for you. This is a coil, which is known as the inductor, which is given the label L. And the units for this are henries. Now, all of these are named after a person, okay? So the person that is responsible for doing the physics and lab work to talk about that component of the circuit. Most of these names and terminologies are almost 200 years old at this point. Then you have this component of the circuit, which is where a charge builds up in the circuit between these two thin metal plates. This is called the capacitor of a circuit. And the units of measurement there, so C is the variable given to that, and the units there are, we call it the capacitance, but the units there are farads. You probably recognize the name Faraday but the units there are farads. So we're measuring, C measures the capacitance. So the capacitance, which is measured in farads. L is measuring the inductance, which is measured in henries. And so this is your EMF. And then finally over here, you've got something which we call a resistor. A resistor, we give the name R to the quantity which we're measuring in a resistor, which is called the resistance. And this is the one that most students are the most familiar with. This is measured in ohms. So what Kirchhoff's law states is your electromotive force, imagine you've got electrons traveling along this circuit. And if you have a charge that starts on the capacitor, then when the voltage kicks on, it causes that charge to start moving. And so one of the important things to note here is moving charge. If you have a moving charge in a circuit, and charge is Q, okay? That's how we will typically notate that in a math course, capital Q. Moving charge is the same thing as current. And I know in a lot of courses you use lowercase I for current. The problem in mathematics with lowercase I is it's also the imaginary number. So in this course, if I talk to you about current, I will use uppercase I when we're building models with it. However, you can't use that in Maple. Can't use uppercase I in Maple because it is reserved. So if you're wanting to model current in Maple, don't call your current function I of t. Choose something else, C of t or just current. You could write out the word current if you want to. But moving charge is current. So moving charge, or the rate of change of charge, is current, which gives us our first fundamental sort of identity between these two things. The derivative of charge is current. Now, I wanted to show you a little image here to explain a little bit more about how a circuit works in the real world. And I wanted to show you an example of an LC circuit, which is a circuit that has a coil and a capacitor, but it doesn't have a resistor. These are some of the more interesting ones. Let's see if I can get that. Why didn't that open? There we go. So this is an image of an LC circuit. And what I want you to see in this image is if you have a charge that builds up between a capacitor and that charge starts to move, then as current gets forced through the coil, it creates a magnetic field. And the magnetic field will cause the polarity to shift, which causes the other end of the capacitor to be opposite in sign to the side that the current started moving through, so that you'll get differing signs on each side of the capacitor, on each side of those plates, which will then repel one another and push the current back the other direction. So what ends up happening is you get current flowing one direction, it gets pushed back the other direction, flows one direction, gets pushed back the other direction, and so on. And this process repeats. In fact, for most transistors which work this way, this process is happening billions of times per second. So this is happening very, very quickly. But to give you a glimpse of something that we're going to talk about later in the course, if you think about this motion of the current, it's moving one direction, then it moves back. It's moving one direction, then it moves back. How is that any different than a pendulum that swings from side to side? Mathematically, there are no difference because it moves to one side, then it moves back. It moves to one side, then it moves back. So that's going to be one of the connections that we exploit to kind of understand how electrical systems behave like mechanical systems. So mathematically, there's no difference between this and a simple swinging pendulum. They're what we call harmonic oscillators in this course, and we'll have a lot more to say about those in the third unit of the course. That just gives you a little idea of the kind of thing that we're talking about here. Okay, so having said all of that, how are we going to use Kirchhoff's law to create a differential equation? Well, it's already an equation. It's what we call a balanced law or a physical law. I need to know what these voltage drops look like in terms of charge and current. And this is a person's physical law that was verified in a lab at some point through, lifetime of study. There are three laws that are of importance here. The first one is Ohm's law. Ohm's law tells you that the voltage drop across a resistor is directly proportional to the resistance and current. So the voltage drop, in other words, the faster the flow through the resistor, the more heat it creates, the more resistance it creates. So if you have a really high current, you'll have a really high voltage drop across the resistor. So that's Ohm's law. You have Faraday's law. Faraday's law states that the voltage drop across a capacitor is inversely proportional to the capacitance and is directly proportional to the charge. So the higher the charge, the higher the voltage drop that occurs across the capacitor. But it's inversely proportional to the actual capacitance, which means that the more the capacitor can hold, the less the voltage drop that will be experienced. Henry's law is the third of these voltage drop laws. Henry's law says that the voltage drop across a coil or the voltage drop across an inductor is directly proportional to the rate of change of current. So as your current is changing, that is going to lead to the faster current changes, which you can think about this as accelerating charge, okay? So if you have an accelerating charge, it leads to a faster drop in voltage across a coil because more of the energy is getting switched to the magnetic field that surrounds the coil, is what's happening there as the charge accelerates through the coil. So those are the three laws, and if we just simply take each law and we substitute it into our Kirchhoff's law. Kirchhoff's law is E is equal to the sum of these voltage drops. In other words, think of it this way. If you're putting in 120 volts into your circuit, then you may lose 60 here, but you've got to gain that 60 back somewhere else in the other two components of the circuit. It forms a closed loop in terms of voltage drops. So wherever you lose voltage, you will gain it back in other places. Now, this is ideal. So this is an ideal model. In the real world, you have insulation and things like that that try to make it ideal, but you will lose small amounts of voltage in your circuit if it's not in an ideal case. So this is in the ideal case, this occurs. But having said that, if we take and plug in each of these laws, R times I, 1 over C times Q, L times I prime, all of a sudden we have a differential equation because there's a derivative quantity and the rest of these are functions of time. The problem is I've got both Q and I in the same problem. So I want to fix that. So written another way here, this is E of t equals R times I of t plus 1 over C times Q of t. And I am going to replace the derivative of I here using this formula. The derivative of I would be the second derivative of Q. So this would be L times the second derivative of Q. And I can do the same thing over here. I can replace this current with the derivative of Q. So I can go in and say that I of t is really just the derivative of charge. And so if you look, we have a differential equation here, but it is a second order differential equation. It's the first second order differential equation I think we've seen in the course. So let me write it out all nice and pretty. It's what's called the LRC circuit equation. It says L times Q double prime plus 1 over C times Q plus R, oops, got that out of order. Typically you write it in descending order for the derivatives. So it'd be R times Q prime plus 1 over C times Q is equal to E of T. So this is the LRC circuit equation for charge. This tells you how the charge in an LRC circuit changes over time. It is a second order ODE. And I know you may be saying, well, we're not studying second order ODEs right now, Dr. Erke, so why do we care about this? Well, we care about this because we can create first order ODEs from this equation. So if you want to create a first order ODE, for example, perhaps the most important first order electric circuit would be what we call an RC circuit. Does anyone know how RC circuits appear in the real world? What are some examples of RC circuits? None of y'all know? I thought y'all were in a circuits class.
Windshield wipers?
You're correct, windshield wipers. And it's because it's a timer, right? So RC circuits are used in timers. That's one of the main uses of an RC circuit. So windshield wipers, little timers. The other place where you will see a RC circuit used quite a bit is what's called a band pass filter. So timers and band pass filters is where you see RC circuits used quite a bit. So how do I create an RC circuit from the LRC equation? Well, you just get rid of L. So if you have a circuit without a coil, then L is 0. And if you make L equal to 0 in that equation above, then you get this one. So oftentimes people will write it this way. And I think you can see once we write it this way, where the designation RC circuit comes from. So that's the most common first order circuit that's out there. Do you see another circuit that we could create? That's a first order circuit. LR. So you have LR circuits. So if I'm going to create an LR circuit, then I can't do that and have it remain first order if I do it in terms of charge. So LR means that C is gone. You don't have the C component. So you're not dividing by 0 here. It's just not a part of the model to begin with. So an LR circuit, you would have LQ double prime plus RQ prime equals E of T. But remember, moving charge is current. So I can write this as Li prime plus Ri equals E of T. And in this form, this would be an LR circuit. Yeah, not super useful. LR circuits aren't a really big deal. There's just not that many of them. I would say the most common place, the most likely place you'd run into an LR circuit in the real world is looking at something like a vacuum tube. Like for a light, not a computer. Like vacuum tube lights have LR circuits in them. Most of them do. But there's just not a lot of great examples of LR circuits. What about the final kind here that I want to talk about? And that, well, let's just talk about an LC circuit really quick. An LC circuit would have what kind of equation? So you'd get rid of R, and you'd have LQ double prime plus 1 over CQ equals E of t, which is Q double prime plus 1 over LCQ equal E of t is typically how you see these written. These are everywhere. Does anyone know what a common use of an LC circuit is? This one's second order, so we're not going to be studying this one just yet, but it will come up later in the course. Does anyone know some LC circuits? Every single one of you is probably carrying an LC circuit with you right now. They're everywhere in your phone. LC circuits are tuners. In other words, they can tune in a specific frequency signal, which means anything that is radio or cell phone in nature has an LC circuit as a part of it. They're everywhere. And this is what I was talking about when I was showing you the harmonic oscillator earlier, talking about the pendulum. So these guys are super important. Pacemakers are LC circuits because they maintain this little back and forth pace, back and forth rhythm. Yeah, there's a bunch of super cool examples that we could get into. In fact, I taught a course, I've only ever taught it once because it was a special topics course called Signals Analysis. We had a bunch of people interested in it. So I taught the course about the mathematics of filtering signals through things like circuits, but more the mathematics behind filtering signals. And it's a very interesting course to take. Those of you that go on to do electrical engineering, that's basically all your graduate school is looking at bandpass filters, frequency filters, tuning filters, things like that, and looking at the mathematics behind those and then figuring out, well, here's what the math says. How do I build the circuit or design the circuit that does what the math says? Very interesting to me at the very least. So here are the two circuits that we're going to be mostly concerned with, right? We're dealing with first order circuits right now. So we're going to be looking at RC circuits and LR circuits, and then eventually later in the course, we'll do LC and LRC. So I just want to jump into an example that's kind of like the example that you have on your Maple Lab due next Wednesday to make sure we're comfortable with what's going on in a circuit problem for now, and head off any questions that you might have. All right. So there's nothing to respond to here, but this is an RC circuit example. I want us to be able to find the function that gives the charge and current after an RC circuit is turned on, where the resistance is 10 ohms, the capacitance is 0.004 farads, and the electromotive force is an alternating current of 85 volts. So you can introduce alternating currents through cosines and sines because they are, oscillating functions. So going back to what I was saying before about having a positive and a negative charge, well, you can think about this function having an 85 and negative 85 in terms of its alternating voltage. I'm going to assume that the switch on the circuit is closed, so we don't close the circuit. We don't start current or voltage being pushed through the circuit until time 0, and that initially there's some small charge on the capacitor. This small charge on the capacitor is going to immediately dissipate. It's the transient thing going back to Wednesday's class. So part of our solution will be how this initial charge on the capacitor dissipates. But I want to point that out once we've done the work in Maple here in just a second. All right, so our example is we know that the relevant information here is we're looking at an RC circuit. We know that the resistance is 10 ohms. We know that the capacitance is 0.004 farads. And we know that the electromotive force is alternating 85 volt source. Okay. So this is literally just plug and play, to be honest. It's a very simple model once we've derived it. We know that our RC circuit model is, that's the one that we just derived it together a second ago right here. So this is the model that we're using. So we know that we've got Q prime plus 1 over R times C. Q equals this. And we're told that the initial charge on the capacitor, so the charge at time 0 is negative 0.05 coulombs. I didn't give you the units for charge and current earlier. I should do that now. The units for current are amperes or amps, and the units for charge are coulombs. So the initial charge on the capacitor is coulombs. So anytime we're referencing the variable Q, that's always the charge that's being built up between these two plates. That's the number that we're constantly tracking. That's what our charge is. When we talk about current, then we'll be looking at the current passing through the capacitor. Actually, it doesn't have to be through the capacitor. We would be checking the current. It depends on what elements your circuit has as to where we're actually calculating the current at. We'll talk more about that later in the course when we do second order models. So here's our example, and like I said, it really is plug and play. We know what model we're working with. We plug the values in. We have an initial value problem. Now, at this point in the course, we don't know yet how to solve this by hand. So this is Q prime plus, if I make this a little bit nicer, that actually this quantity turns out to be 25. So our differential equation, while very nice, is linear, which means it can be solved, but we haven't really talked about how to solve it yet. So we're going to have to rely on Maple here. I just want to reinforce once again what it means to be linear. So this is a linear function of Q. So if you look, this is like AQ plus B, right? That's how that right-hand side is written. So Q prime equals AQ plus B, where A and B are potentially functions of time, but Q appears as the linear, as the only dependent variable over here in this form. So this is a linear function of Q, so this is a linear model. All right, let's take a look at it together in Maple, and we'll just walk through a couple of things, and if you have questions, feel free to jump in and ask. So I'm going to start by naming my RC circuit model. Let's see, we've got the derivative of Q plus 25Q is equal to 85 cosine 150T. Okay, and I could do a desolve on that. So I could solve my RC model together with the initial condition. To get the solution. So here's the solution, and I just want to point out a couple of things about this solution. So let me kind of switch over to text so I can just type this in. we talked about in class how there are always two parts to a solution. There's a steady state part and a transient part. So every linear differential equation, every solution to a linear differential equation has to have both behaviors. So if you look at the solution for charge here, can anyone tell me what part is the steady state part? Steady states we typically associate with oscillations. Where's the steady state part? The first two terms. So these first two terms represent the steady state part of the problem. So I'm just going to copy and paste that right there. That's our steady state part. The transient part is the part that's responding to that initial condition. So the initial charge goes away according to that function. So, you know, just to make sure that we're okay with this, just make sure I write it in. This models how the initial charge dissipates over time. Whereas this models how the charge in the capacitor reaches a steady oscillation state eventually. So eventually we get this steady sort of oscillation state in our capacitor, and whatever initial charge there was on the capacitor, this transient part of the solution models how that initial charge dissipates over time. Let's just see a plot of it. This will make a lot better sense if we plot it. So I'll go back into math mode, and I want to plot the right-hand side of that function number 2. And we'll look at it for, like I said, this happens very quickly, so I wouldn't choose a particularly large value of time. Time here would be in terms of seconds, most likely. I didn't give you any time, but it would definitely be in terms of seconds here. So let's look at it for 20 seconds. And you see how many times it oscillates back and forth in 20 seconds. So this is why I said you need to be very careful about the time you use for a circuit, because remember, these things oscillate very, very quickly. So let's look at it for the first 2 seconds. So even over the first 2 seconds, you can see that it starts out at an initial charge of -0.5, and then it immediately bumps up, and then it kind of levels off at some point. So I'm still not seeing a lot of great information. I'm going to make it smaller. This is over the first second. Now maybe we've got a little bit better view of what's going on. You see how you've got the negative exponential here, but it's a negative exponential, so it's actually decayed that's turned up. So this thing eventually dissipates, so the charge is allowed to resume to a higher level, and then at some point it just settles into a steady state. So you can see here, and we'll be able to calculate this exactly later in the course, you can see here that after a certain amount of time, the effects of the transient have worn off, and this thing is just a steady state oscillation. You can see that that's somewhere between 1/10 and 2/10 of a second is where that, it's basically unnoticeable at that point. We'll have a way of calculating that later in the course. But beyond that, it's just simply oscillating back and forth. So if I wanted to ask at this point, what is the charge on the capacitor for this problem? How would we, or excuse me, what is the charge oscillating between? In other words, what is the amplitude of the charge in steady state? How would we answer that? So what I'm after here is find the amplitude of the charge in its steady state. Well, here is the steady state, the thing that models the steady state. Luckily for us, that is a sinusoid, so it's an oscillation. And you should remember from pre-calculus that anytime you have two functions which oscillate with the same frequency, so sine and cosine are both oscillating with the same frequency, that they create one wave. We can see the one wave that they create here. which means there's a single amplitude that wave carries. It carries a constant amplitude. I'm not 100% certain that you remember how to find those, so I wanted to go over it with you today. The coefficient of the first oscillation here is 17/185ths, and the coefficient of the second oscillation is 102/85ths. Do you remember how you can take those? Do you remember what the formula is to take those two numbers and come up with a single number that describes the oscillation of this wave? Do y'all remember the formula for that? It's the square root of a squared plus b squared. So there's your amplitude. Let me evaluate that. To get a decimal. So it's approximately 0.56. And you can see here that that is this number here. That's the very top. That's the amplitude. It gets up to a height of about 0.56 over time. So the largest charge we would expect to have eventually in the circuit is 0.56 coulombs of charge. And it's, you know, if you're the one that's designing the circuit, then it's up to you to know whether or not that's too much charge or not enough charge. Does that make sense? Now, what if we wanted to talk about current? How would we talk about the current of what's going on in the circuit? Well, we have the charge, and we know that the derivative of charge is current. So if I just take this function and I differentiate that function with respect to time, that's got to be current. So my current as a function of time is given to me by the derivative of the charge. Okay. So my current function is given by this. So there's your current, and I could plot the current over the first 2 seconds as well. And you notice that it comes down a little bit, but I'll shorter value here. So there's how your current will change over time for this circuit. So it looks like we're slightly above 80 amps. So we'll oscillate back and forth a current of about 80 amps throughout this circuit. Do y'all have a question related to that? Do you have any questions related to this problem for me? This is what I'm expecting you to do on the Maple Lab for circuit problems this week. All right, well, if there's no questions, I want to quickly jump into a discussion of kind of setting up our discussion for Monday, which is going to deal with integrating factor method. Y'all are quiet today. So either I'm telling you something you already know, or I'm telling you something you don't care about, or I'm telling you something that's so hard you don't know what to ask, or maybe it's none of the above and y'all are just ready for the weekend. All right, so I want to talk about a little bit, just some terminology here to set us up for class on Monday. All of the equations that we've talked about that are linear have this form. So this is what we call the general form of a linear ODE. It almost looks like a polynomial, right? So it's like the derivative is like y squared, y, and then the constant terms. So you can kind of think about it like a derivative. In fact, we're going to use that to our advantage in the second and third units of the course. So if I ever ask you to write down the general form of a linear ODE, that means take all the terms to the left-hand side and write them in descending order of the derivative. However, the most common form for us is what's called the linear form or the standard form. Either one of these two forms here. Fit them all on the same page? No. So you've got the general form. So if you take the general form and you divide through by A, then you've got B of t divided by A of t. We're going to call that P of t. And you've got C of t divided by A of t. We're going to call that Q of t. Well, technically, it's the negative of both of those. But these are two different forms that you can get from that. So this one's called linear form because the right-hand side looks like a linear equation in terms of y. And this is called the standard form because this is the form that's easiest to find integrating factors from. It's the standard form we use in the text. Now I want to caution you because in Monday's class, when we start talking about integrating factors, your textbook uses this form. And I don't like using that form because if you use that form, the very first thing you do is move it to this form, which makes the P of t negative. And I don't want to have to deal with negative numbers if I don't have to. So I will be using this standard form in class on Monday to determine what an integrating factor is with you, okay? Now, in this form, there are two different types of linear equations. For starters, this thing can always be solved. That's what makes linear equations the most valuable equation to look at in this course. For starters, they model a ton of stuff. We've already seen how it models circuits, cooling problems, mixing problems. That's just the tip of the iceberg. Linear equations model a lot of stuff, but they can always be solved. So if you come up with a linear model, you don't have to worry about whether or not you can solve it because solving linear models turns out to be really easy compared to other kinds of models we'll encounter in the course. But there are two types of linear models. There are linear models where the right-hand side is 0, which means the model is homogeneous. You can think of it this way. Q of t would be like the voltage source. The voltage source is what drives the current around the circuit. So we oftentimes will call Q of t the forcing function or the driving function for the differential equation because it drives the thing that's happening in the model to actually occur. Without Q of t, the model is it's just that transient term that dissipates. There's no steady state. There's nothing interesting going on because there's nothing forcing it to turn into a steady state. Think of it this way. I like to think of these problems as a swing set. So if you're the person pushing someone on a swing, then the person will swing back and forth. But if you're not there, what happens is the person kicks themselves off the ground. That's their initial condition. And if there's no one there to push them, eventually they just kind of go back and forth and stop if they're not trying to push it themselves. But if you have someone pushing the back of someone that's on a swing set, then eventually whatever pattern that person was swinging at, they will adjust to the pattern you're pushing at. So you have a forcing term on the right-hand side that's called the homogeneous or inhomogeneous term. So if this term is not 0, then the equation is called inhomogeneous. So what we're going to have to do this semester is when we encounter linear equations, we're going to have to always solve them twice. We're going to have to solve them once for what they do without the homogeneous part. That's the transient part we're studying for. And then we're going to have to solve them again for when the Q of t is there and figure out how they respond to that part. That's the steady state part. So we're always going to have to solve these kinds of differential equations twice. I think that's a good stopping point for today, primarily because we're out of time. But what we're going to do at the beginning of class on Monday is we're going to figure out a formula for P of t and Q of t that involve P of t and Q of t that will always let us solve these first order equations. And that's called the integrating factor formula. All right. Thank y'all for showing up this morning. I'll be in touch with you soon. I'll see you again on Monday. If you have any questions this weekend about the exam or any of the assignments, let me know. Y'all have a good one.
Thank you.
You're welcome.
Thank you.
See you, Michael.